Namaste. Um, so today our discussion is tangent wedge method and tangent cone method, right? So it's an interesting topic again. So far what we have done is we have considered various methods for the calculation of coefficient of pressure, right? I hope you remember the tangent wedge method. The Newtonian method. You have already considered the inclination angle, right? And from the inclination angle, then you have calculated the Cp, that is equal to 2 sine square theta, right? So in this method, maybe the tangent wedge method and tangent cone method, we will arrive to it is not uh, it is just a method which can yield somewhat good result, but not with a very higher classic theoretical background actually, right? So let us consider this method. It is an easy and interesting method, and it is also an approximate method, right? So I acknowledge John D. Anderson hypersonic and high temperature gas dynamics, right? So in all our previous discussion, we are trying to predict the hypersonic flow behavior, right? So based on the knowledge of the inclination angle, right? So how much it is inclined to the relative free stream, right? So one good example we can consider is the Newtonian theory, where I hope you remember in the Newtonian theory we consider an plate, right? Such plate inclined at an angle theta, right? So we have considered okay, this is theta, and we have a free stream velocity v infinity, and we have done, when it hits, it moves tangential to the plate, and all those information we have done, and finally we have arrived to the calculation of Cp, that is equal to 2 sine square theta. Okay, so now we will use the similar principle of inclination angle, right? So the inclination angle, what is the inclination angle, right? And how can we calculate the coefficient of pressure, right? So all those we will check now. So you can hear me, right? Yeah. Okay. Now, so let us consider the tangent wedge method, right? So it is applicable to the two-dimensional hypersonic body. So tangential wedge method, it is applicable to two-dimensional hypersonic body, but the tangential cone method, we can consider the three-dimensional hypersonic body. Okay. So let us consider this two-dimensional body. So you see the actual body is having this hatched lines, right? So this is the actual body, right? Now assume that the nose of the body is pointed, right? So the nose of the body is pointed here, right? So at this point, the nose is pointed, and from that, if you say we can consider the local inclination angle theta at all the points along the surface, right? It should be less than the maximum deflection angle for the free stream. Say you can say this particular point, you have an angle theta I, and here if you say, and if you draw a tangent, it is also another theta. So like that you can draw all the thetas, right? And if you consider this particular point, if you draw a tangent, that will become the maximum local deflection angle, right? So local deflection angle, that is the nose, will be very much greater since it is a pointed nose. Right? So in the last class also you have tried that Cp versus theta. for Newtonian, modified Newtonian and Newtonian Boltzmann theory, and you have plotted a graph, right? So you know very well that at the nose, the maximum local deflection angle. Now, ultimately, we need to calculate the pressure at point I. Let us consider this point I on the surface. And given is a free stream Mach number m infinity, right? Now, the point is, okay, I said like consider the point I on the surface of the body. We wish to calculate the pressure at point I. And let us consider the flow deflection angle, local deflection angle is theta I. Now, imagine a line drawn tangent to the body at point I. Okay. So, you see here you have a theta I and the point I. Now, we draw a tangent here. Right. So, this is a tangent. So, this tangent which creates an angle theta I. Okay. So, here the point is this body shape is the original shape or the actual body. When you draw the tangent for this particular point I, that is the equivalent semi wedge for point I with the deflection theta. Okay, I hope you understand this point. Now, assume that I consider this particular point. So let me draw a tangent. Say I call, okay, can we do in the other side? Say we have a particular point here and I consider this point as J. Now I draw a tangent. If I draw a tangent, then this particular theta is theta J. Okay, for the point J. Let us consider the point J. So like that it goes, right? So theta J will become equivalent semi-wedge angle. So I can write here that this angle is theta J, and I can say that this is similar to this equivalent semi-wedge angle at point I. Instead, this become an equivalent semi-wedge for point J with angle theta J. So this theta I, theta J, I want to show it for your reference, right? Now, we can consider this as a wedge, right? We have considered this as a semi-wedge anyway, right? So, if you know the semi-wedge with the deflection angle theta I, from the oblique shock relation, you can draw the wedge, right? I mean wedge shock. So this is a wedge shock that you know that the wedge shock is beta, correct? Beta angle. Right? Beta is a shock angle, or we can call this as a wedge shock, whatever it is. So this is the procedure. You have an actual body, and every point I, j, k, whatever point you want, you can take it. You can draw a tangent, and that tangent makes an angle theta to the horizontal, and then we can call that particular angle as equivalent semi-wedge, right? Equivalent semi-wedge for particular point I or j or k with a deflection angle j or k. So for a particular theta I, j, k, whatever it is, we can draw the wedge shock, right? We can draw a wedge shock. That is the equivalent wedge shock, we can say. See, please remember, if you have a kind of pointed nose and if you have actual body, your actual bow shock or body shock forms like this. But now, in order to calculate the pressure at the point I, we make an approximation, right? So tangent wedge approximation assumes that the pressure at point I is same as the surface pressure on the equivalent wedge at the free stream Mach number M1 or M infinity, right? So Pi is obtained directly from the oblique shock relation for a deflection angle theta I and then given Mach number, right? Because we know already I and we know theta I, and of course we can draw the wedge shock based on the oblique shock relation, and now we say that this Pi also can be calculated from the oblique shock relation, right? Again, tangent cone method, I told tangent cone method can be equated for the axisymmetric bodies or three-dimensional bodies, right? It is almost analogous to the tangent wedge method, right? So let us say we can consider a point I, j, k, whatever point you want, and you draw a tangent. Now this become a three-dimensional, hence we consider it is not equivalent wedge, but instead it become an equivalent cone, right? And that makes an angle theta I, correct? And that creates a cone shock. There it is wedge shock, but here it is the cone shock. And from that we can calculate from the cone table. There is a table called cone table where you can calculate the pressure at point I, Pi, right? So similar procedure we follow. Okay. Now, so we know the equivalent wedge and equivalent cone, and from that we can calculate the pressure at point I from the oblique shock relation and the cone shock, right? So both the tangent wedge and tangent cone methods are actually the straightforward methods, right? So they are approximate methods, but not based on any theoretical backgrounds, right? That we need to remember. That is a big limitation for this tangent wedge and the tangent cone method, right? We cannot derive these methods from a method model of the flow where the basic mechanical principles are applied, right? So it is almost like in the case of Newtonian flow, we have a theoretical basis, right? But this one is very much approximate, right? And hence it does not have any theoretical basis. Okay. Now let us go a little deeper. We have this cone method, right? So let us consider this particular area, right? Let us zoom this. Okay, so we have zoomed this. So you know that this I, that is our intended pressure point Pi, and the point P, we note this point B as a wedge shock, right? Point on the wedge shock, and A is the particular point on the body shock. I hope you remember what it is. So this is a wedge, and this is a wedge shock. This is a equivalent semi-wedge, and here you have a body shock. So what we are doing is we zoom this particular part, and we will see, right? So let us consider a line drawn perpendicular to the body surface at point I across the shock layer. So if you draw across the shock layer, according to our discussion, there will be a wedge shock and it ends in the body shock. Okay, the angle which is made from the horizontal surface to the wedge shock is beta wedge, because this is a shock angle, right? And here you have a body angle, body shock angle. So we can say that the body shock angle is greater than the wedge angle, right? Now, so note that the imaginary shock wave from the imaginary equivalent wedge crosses this line, that and all we had a discussion. Right? So in this we can say that in hypersonic flow across an oblique shock wave on a slender body, the y component of the flow velocity v is changed much more strongly than the x component. So ultimate point is the v component changes very much than the u component. Don't ask me, sir, how it comes, because we will spend little time little later on all this discussion. But now we will have a small approximation. Okay, so you need to remember that in hypersonic flow across an oblique shock wave for a slender body, the y component dominates than the x component. This is the y component, and this is the x component. So the x component, y component dominates than the x component, right? That is what we need to remember. Let us discuss this little later. Okay. So a simple discussion that we know, if we consider m infinity tends to infinity, and we can write u2 by v infinity is equal to 1 minus 2 sine square beta by gamma plus 1. And similarly, we can write v2 by v infinity is equal to sine 2 beta by gamma plus 1. Right? So we can represent this based on the oblique shock relation. What is v2 and what is u2? So v2 and u2 can be represented here. Now u2, so we want to calculate del u by v infinity. So that is proportional to v infinity minus u2 by v infinity. So we can approximate that to gamma plus 1 by 2 into theta square, whereas del v, right, the y component, that is proportional to theta. Right? You can arrive to this particular point from this equation by considering m infinity tends to infinity. Right? So here you can note one thing, del u, which is the change of velocity in the x component, which is proportional to theta square, right? And del v is the change in y component, that is proportional to theta, right? Del u is proportional to theta square and del v is proportional to theta. So clearly we can say that the change in velocity, correct? Okay. The change in velocity is considerably smaller, right? The change in velocity is considerably smaller in the case of u, but in the case of v, del v, it is proportional to theta. So this is of the order theta square, and the change in velocity at u is theta. I mean, this will become v, right? This v is the velocity and u is the velocity which is proportional to the theta square. Okay. The change in velocity u is considerably smaller when compared to the change in velocity v of order. Right. Okay. Now, now let us recall the Euler equation. We know that Euler equation which shows that the dP is equal to minus rho v dv, right? So this means that the meaning of this is that the pressure gradient, right? The pressure gradient normal to the flow, right? So the principal change in pressure is therefore normal, right? This is therefore along the normal line IAB, right? What is that IAB? This is normal This is IAB. This is IAB. So this normal line, okay. So this is the representation of this normal line. So we can say that the principal change in pressure is therefore along the normal line IAB. By comparison, changes in the flow direction are of second order. Okay. So here we examine the figure, and the pressure, the surface pressure on the body I is dominated by the pressure behind the shock at point A, right? See, you know very well that if this is the consideration, if the body shock is the consideration, then necessarily this particular fluid element, you need to consider the R here, and the centrifugal force effect we need to consider, right? Centrifugal force effect. So here, because of the centrifugal force effects, the pressure at point I, PI will be definitely less than PA, because PA consists of, say, if we consider the Newtonian Boltzmann, you have the Cp sine square theta plus the centrifugal component, right? Centrifugal component, right? So now in tangent wedge method, if we consider Pi is equal to Pb, where Pb is the pressure behind the imaginary shock. Right? So the pressure Pb is already less than Pa because of the body wedge angle is greater than, I mean, the body angle is, shock angle is greater than the wedge angle, right? Shock wedge shock, right? So we can see that finally the wedge pressure Pb is reasonably good to approximate as a surface pressure Pi, because in the real flow picture, the high pressure Pa behind the body shock is mitigated by the centrifugal effects, right? So we can say that Pi can be calculated from Pb, right? So the same reasoning holds good for the tangent cone method also, right? Fine. So a simple overview. Let us have an overview. So here you have an actual body. So in the actual body, you want to calculate the pressure at point I. Then what you have done is we have drawn a tangent from that particular point that creates an angle theta I, right? So now it become an wedge, right? It is considered as a equivalent semi-wedge, and from the equivalent semi-wedge for point I with the deflection theta I, that creates an wedge shock. Say the wedge shock we can draw, and here the beta is a wedge shock, and this is a wedge, shock angle. And if you consider a particular point here and draw, this is a beta body, right? So we know that the point here, Pi is more or less equal to Pb, because we consider B here and this is A, right? That is a approximation where A always includes, Pa includes the pressure at the point I as well as the centrifugal effect, right? Centrifugal effect, and hence we finally conclude that the pressure at the point I can be equated to pressure at point B. All right. So I hope you remember this particular point I. Point B can be equated to pressure I, Pi, right? And we had a discussion that In the case of hypersonic flow, cylinder body, the Y component of the flow is changed much more than the U component. That is what our finding in this particular lecture. Okay. So finally, we equate Pi is equal to Pb because Pa cannot be considered since this is the centrifugal effect need to be included, right? So this is what the basic discussion about the tangent wedge and tangent cone method. Thank you very much. I stop at this point. So I recommend you to go through once. I recommend you to refer John D. Anderson hypersonic and high temperature flow for reference. Right? Thank you very much.